Hello viewers, welcome back to this channel. So in this video we are going to be starting the first video that is going to be covering the topic of thermochemistry as required by the NCDC about advanced level. So this video is specifically for students in senior 5 and senior 6, and you are advised to subscribe to the channel and share the video to your friends so that you can all benefit as a family. So thermochemistry can also be called chemical energetics, but here in A-level specifically, we refer to it as thermochemistry. Now thermochemistry often appears in each and every paper of UNEB, and it's a fundamental topic to be required for you to pass your U.A.C.E examination. So we're going to first start by defining what thermochemistry is about, as we covered it at O-level. So you're saying that thermochemistry is going to be defined as the study of heat changes or enthalpy changes that accompany a specific chemical reaction. And here we are going to be terming it as chemical energetics or thermochemistry. And we are saying that chemical reactions are accompanied by evolution or absorption of heat energy, and therefore the energy changes that may occur may either be exothermic or endothermic. So you're saying that the quantity of heat that is given out or the quantity of heat that is being absorbed during a reaction is going to depend on a number of factors, and some of the factors are going to include the following. So factors, we are going to call those ones as factors that affect enthalpy of a reaction. Now enthalpy of a reaction is denoted by delta H. And you're going to be saying that the first factor is going to be the amount of reactants or products that are going to be involved in a specific chemical reaction. And you're saying that it's going to be necessary to code that heat changes to specific molar quantities of either the reactants or the products. For example, heat of combustion of 2 moles of hydrogen is going to be double than that of combustion of 1 mole of hydrogen. So one of the factors affecting enthalpy of this reaction is going to be the amount of reactants or products that are involved in a specific chemical reaction. And then Roman number 2, we are going to be looking at the physical states of the reactants or products that are being involved in a specific chemical reaction. And we are going to be saying that the enthalpy of a reaction is going to depend on the physical states mainly of the reactants and the products. For example, when hydrogen and oxygen gases combine to give liquid water, the heat of combustion is going to be, or the heat of the reaction, or the enthalpy of reaction is going to be different than when they combine to form gaseous water. So you're going to have the first equation where hydrogen is burnt in oxygen to form water, but this water is in terms of liquid form. So when you form water in liquid form, enthalpy of combustion is going to be equal to negative 286, and this means that energy evolved is 286 kilojoules per mole. The negative under enthalpies implies that energy is being evolved, or such a reaction is exothermic. But however, when we heat hydrogen in oxygen and we form gaseous water, we are going to be forming the enthalpy of combustion or the enthalpy of reaction or the enthalpy of formation of our water is going to be equal to negative 242 kilojoules per mole. And this means that 242 kilojoules per mole of energy are being evolved. I've said that the negative implies that it's exothermic reaction. If it was positive, it means that it is an endogenic reaction. And that means that that's a reaction that takes in energy. So you're going to note that the temperature at which the reaction is taking place must be specified, and usually the standard temperature is always 25 degrees Celsius. Now 25 degrees Celsius in terms of Kelvin, you just add 273, and in terms of Kelvin it's going to be 298 Kelvin to be used. So for any standard reaction to take place, it must be carried out at a standard temperature, which is always 298 Kelvin. And also the pressure at which a standard reaction is taking place must be specified. For example, most of the reactions that are standard take place at 1 atmosphere. If you don't, 1 atmosphere is equivalent to 760 millimeters of mercury when used in determining enthalpies of formation of standard reactions. Now we are going to start with standard enthalpy changes, and we look at the definition of a standard enthalpy change. But before defining it, let's first look at what a standard enthalpy change or a standard enthalpy of a reaction means. So we're going to be saying that since the heat of a reaction varies with temperature, it is important to have a fixed standard temperature or a fixed reference state. And we are saying that a substance is said to be in its standard state if at all it is present in its most stable state at the standard temperature, which is always 298 Kelvin. Now remember that this is called the standard temperature because it's coming from the room temperature, which is always 25 degrees Celsius. And the pressure must strictly be 1 atmosphere. And we say that 1 atmosphere is equivalent to 760 millimeters of mercury. So therefore we are going to start to define standard enthalpy change or standard enthalpy of a reaction as the heat change that occurs when molar quantities of the reactants that are present in their normal physical states react to give products under standard conditions, and those standard conditions are going to be of 1 atmosphere, and 1 atmosphere is going to be equivalent to 760 millimeters of mercury, and the temperature must either be 25 degrees Celsius or 298 Kelvin. So those ones are the standard conditions. So standard enthalpy change is the heat change when molar quantities of reactants that are present in their normal physical states react to give products under standard conditions of 1 atmosphere and 298 Kelvin. And you're going to be saying that this is going to be denoted by delta H, standard note, and the subscript of R. So that whenever you see this symbol, it's going to represent standard enthalpy of a reaction. And we are going to be putting this R here to define that this is going to be standard enthalpy of a reaction. The alpha above here in terms of powers is representing that this is going to be a standard reaction. So we are going to say that depending on the type of a reaction, different enthalpy changes can take place, and they include the following. And we are going to be commencing with standard enthalpy of combustion. So definition of the standard enthalpy of combustion, every definition that we are going to be defining containing this word of standard must have conditions that must be in standard form. And that is to say standard temperature and standard pressure. And pressure, which is standard, is 1 atmosphere. Temperature, which is standard, is 298 Kelvin. So defining standard enthalpy of combustion. Now, standard enthalpy of combustion is not the heat change, as most of you define it and you lose marks. Everything involving combustion always gives out energy. So we define it in terms of heat given out when 1 mole of a substance is completely burnt in oxygen under standard conditions of pressure and temperature. Now a student here can either specify them or he can just say under standard conditions of temperature and pressure. If specified pressure must be 1 atmosphere and if specified temperature must be 298 Kelvin. Now proceeding, we are going to say that in all combustion reactions, heat is given out. That's why when you are stating the definition for enthalpy of combustion, we always start with heat given out. It's not enthalpy change, it's always heat given out. Standard enthalpy of combustion involves heat given out. That means that on all the reactions that are involved in combustion, their signs must be negative. The signs next to the values must be negative, and the negative simply indicate that energy is being evolved, or such a reaction is exothermic. So this is the standard enthalpy of combustion of carbon, because carbon is being burnt in excess oxygen to form carbon dioxide gas. And also here, this is the standard enthalpy of combustion. You see here the C is representing standard enthalpy of combustion, and you write down the name of what you are combusting or what you are burning, and here we are burning methane. So standard enthalpy of combustion of methane is negative 890 kilojoules per mole, and it's according to this following equation. Whenever you're dealing with chemistry, you make sure that the states are well presented. And after states being well presented, you make sure that equations are also well balanced, together with the letters being written properly. So let's look at an experiment to determine the enthalpy of combustion of any given substance. So here we are going to be saying that the experiment is performed using a bomb calorimeter. It consists of a strong sealed steel vessel or bomb enclosed in an insulated water jug. So you're going to be saying that the energy released during the combustion is going to be transferred directly to the water jug, and the temperature rise is going to be measured. And this temperature rise is what is going to be our enthalpy of combustion of that given substance. So looking at the procedure, we are going to be saying that a known mass of a substance, such as an alcohol, like ethanol, is going to be placed in a crucible. A crucible can also be defined as a simple dish, as we are going to look at the setup. So we get a known mass of an alcohol into a crucible, or someone, if I thought the spelling is very hard, you go with a sample dish. And then after that, we suspend it in a steel bomb. The bomb is then going to be filled with oxygen and is going to be massed in a calorimeter which is containing a fixed volume of water. The volume of water that is present in the calorimeter must be known according to the procedure. For example, it must be V centimeters cubed. And we are saying that the temperature of water before the experiment starts is going to be recorded and is also going to be recorded at intervals. And the average temperature is going to be calculated, and this becomes the initial temperature of water. So before starting your experiment, you make sure that you immerse your thermometer into the given volume of water that you are using in the bomb calorimeter to determine the initial temperature of water as your T1 degrees Celsius. So proceeding, we are going to be saying that the substance is then going to be ignited by simply passing a current or an electric current through a firing circuit. And by doing this, the substance is going to burn, and the heat generated is going to increase the temperature of the surrounding water that is present in the bomb calorimeter. So what is done is that as the temperature of water present in the bomb calorimeter is increasing, we get the maximum temperature. This word is very important because time comes and then the temperature falls down, but we capture the temperature at which the mercury in the thermometer has reached to. So we capture the maximum temperature of water and then we note it down. And that's going to be your final temperature, which is going to be T2 degrees Celsius. Remember that we already got the initial temperature as T1 degrees Celsius. And the setup is going to be as follows. So the ignition wires are going to be going to the crucible or sample dish. And then the crucible sample dish is going to be containing our sample, which we say the given mass of an alcohol. And this is going to be placed in a steel vessel or a steel bomb calorimeter. And after this steel vessel is going to be massed in this calorimeter, but this calorimeter must be containing a given volume of water, together being fitted with a stirrer. Now the reason why you fit it with a stirrer is to ensure uniform distribution of heat. And this steel vessel or the steel calorimeter must contain an oxygen inlet, because oxygen is the one which allows combustion of any given substance to take place. So everything is going to be fitted within the big bomb calorimeter, and the thermometer is going to help us determine the temperature changes when we apply a given amount of heat during combustion. So going to treatment of results, we are going to be saying that if M is going to be the mass of water that we used, and then C is going to be the specific heat capacity of water that is present in the bomb calorimeter, then change in T is going to be the rise in temperature, and you are going to get it by simply getting the final temperature, final maximum temperature, minus the initial temperature of our water. And then W is going to be the molar mass of the given compound, together with M or small m is going to be the mass of the compound or the sample that was burnt in the crucible or in the sample dish. So the assumptions that are going to be involved in such an experiment is that heat evolved by burning our sample or by burning our compound is going to be equal to all the heat that is being gained by water that is present in the calorimeter together with the bomb calorimeter. So the heat evolved or heat of combustion evolved from burning the sample is going to be equal to the heat gained by both the water and the calorimeter together with the steel vessel or the bomb calorimeter itself. And we are going to be saying that the heat gained by the calorimeter is going to be negligible, and so the heat lost by burning a compound is going to be equal to the heat gained by water. So we assume that the heat that is being gained by the bomb calorimeter is going to be negligible since the calorimeter has a very thin surface. So we assume that all the heat that is being produced from combustion is going to be equal to the heat that is being gained by water. And to get heat that is being gained by water, we get mass of the substance times the specific capacity times the temperature change. And this heat is going to be measured in joules. That's why we are putting this J here. But remember that we use the given mass of a substance, but we need to convert the mass into moles. So to convert any mass into moles, we get the given mass divided by the molecular mass, and we say that W is going to be the molar mass of our compound. So that's why you're having here M divided by W, and we convert that mass in terms of moles. So that's why we are going to have small m divided by W. That means that you're converting given mass into moles. That's why you're writing this word here, moles. So M divided by W moles of a compound are going to evolve this kind of heat. Then what about 1 mole of a compound? Because when you're defining standard enthalpy of combustion, we said it must be 1 mole of a compound to be burnt. So what about 1 mole of a compound is going to produce which heat? And that is going to be MC times delta T multiplied by W divided by M. And to remember that this heat is going to be measured in joules. To convert this heat into kilojoules, we divide through by 1,000. So that's why you're having this expression divided by 1,000 multiplied by m in terms of kilojoules. And this is going to be our standard enthalpy of combustion of such a substance. So you're going to say that where this heat released per mole is the standard enthalpy of combustion of any sample substance that you are being told to do the experiment with. Now in UNEB, or if at all it's examined, they will be specifying the sample substance you are going to use. For example, they may tell you propanol. So the procedure remains the same, but you'll be specifying the substance of combustion. Now another enthalpy change that you are going to be looking at is going to be standard enthalpy of formation. And you are saying that here, hypothetically, all compounds are formed from their constituent elements, and therefore the enthalpy change accompanying those processes is going to be called enthalpy of formation. For as long as we are having any compound that is being formed, the heat evolved is being called enthalpy of formation. Now we are saying that here, the enthalpy change when 1 mole of a compound is formed from its constituent elements, provided that these constituent elements are in their normal physical states, or they are in their normal standard states, under standard conditions of pressure and temperature, is going to be known as standard enthalpy of formation. So redefining this standard enthalpy of formation in case you are examined, because this is a common concept under examination bodies. So standard enthalpy of formation is going to be that enthalpy change. We are saying that it's going to be enthalpy change because it can either be endothermic or exothermic. So it's better you just write enthalpy change. When 1 mole of a compound is formed from its constituent elements, provided that the constituent elements are in their normal physical states under standard conditions of temperature and pressure, and it's going to be known as standard enthalpy of formation. And the denotation for that is going to be delta H with a standard or with a fit above, and F in the subscript to show that we are handling standard enthalpy of formation. Now here, a standard enthalpy is of formation of varying products. Now notice that standard enthalpy of formation only involves compounds. You cannot have an element and you say that it's going to have a standard enthalpy of formation. Now for elements, their standard enthalpy of formation is going to be equal to 0 because there is no way we can form an element. They just exist in nature. So if you burn hydrogen in oxygen, you're going to have your standard enthalpy of formation of water to be negative 286 kilojoules per mole. And if you burn carbon in oxygen, the standard enthalpy of formation of carbon dioxide is going to be negative 393 kilojoules per mole. And if you burn sodium in oxygen or in limited oxygen, you're going to get sodium oxide. And the standard enthalpy of formation for sodium oxide is going to be negative 416 kilojoules per mole. Now we have made the note here that the enthalpies of formation are not measured. They are not measured stroke determined, but experimentally, enthalpies of formation are not measured or determined experimentally, but are determined indirectly, as we are going to be looking at the calculations under it. And we are saying that here, the heat of formation of a substance is going to be related to how stable a compound is. That is to say, if I tell the enthalpy of formation at the end of your calculations, if you get it in terms of negative, that compound is going to be very stable. That's why we are saying that here. For example, compounds formed exothermically, or if you calculate the enthalpy change or enthalpy of formation of any compound and you find that it's exothermic, or the energy value that you have got is negative, such compounds are at lower energy levels. They are at lower energy levels than their elements, and therefore they are more stable than the compounds that are formed endothermically, if any is present. So if at all your final answer of enthalpy formation, you have calculated it to be negative, that means that such a compound is very stable and such a reaction is very feasible or is very spontaneous. All those ones mean that such a reaction is very possible. But if at all your standard enthalpy formation is positive or endothermic, that means that such a reaction is not spontaneous, or such a reaction is not feasible, or such a reaction cannot proceed at ordinary or room temperature, and therefore it cannot take place. So proceeding, we are going to be saying that the elements in their standard states are chosen as reference points, and therefore by conversion or by conversion, their standard enthalpies of formation is 0. Like I said, elements just exist. There is no way you can form an element. So that means that anything that exists in its standard state, for example, gases, anything that cannot be formed by reacting two elements, its standard enthalpy of formation is going to be 0. For example, gases like oxygen, gases like nitrogen, elements like magnesium, elements like nitrogen, all elements, their standard enthalpies of formation is 0 because for them, they just exist in nature. There's no way you can form them. So they don't have any standard enthalpy of formation. Now let's look at the laws that are involved in thermochemistry. Now we are saying that there are two laws of thermochemistry that are involved in this topic. And we have the Hess's law and then the Laplace's law. So starting with the Laplace's law, we are going to be saying that the first law is going to say that the amount of heat used to decompose a compound into its specific elements is going to be equal in magnitude but opposite in the sign to the heat given out when a compound is being formed. Amount of heat used to decompose any given compound into its elements is going to be equal in magnitude but opposite in the sign to the heat given out when a compound is being formed. And you're saying that this is going to mean that when a chemical reaction is reversed, the sign of the enthalpy of reaction is going to be changed. For example, if at all you're having carbon dioxide decomposing to give us carbon and oxygen, the sign is going to be positive. But if at all we reverse this reaction in terms of carbon reacting with oxygen to form what was our reactant before, carbon dioxide, then the sign changes from positive to negative. So what you should note here, or what is the takeaway here, is that whenever you reverse a reaction in thermochemistry, the energy change or the sign on the energy value has to change. If it was positive, it turns to a negative. If it was a negative, it turns to a positive. Now looking at the second law, now the second law was discovered by Hess, and we are going to be calling it as Hess's law of constant heat summation. And this is the law that is highly examinable in UNEB. So we're going to be saying that according to Hess's law, it says that if a reaction is carried out in a series of steps, the enthalpy change for the overall reaction equals to the summation of the enthalpy changes for the individual steps, provided it's at a constant temperature and constant pressure. So such a reaction, if a reaction is carried out in a series of steps, the enthalpy change for the overall reaction is going to be equal to the summation of the various enthalpy changes that are involved in such a reaction of the individual states or of the individual steps, provided that such a reaction is carried out at a constant pressure and a constant temperature. So that's the second law, and it's the second law of Hess, which is called Hess's law. So having an elaborative explanation for that, what Hess means is that if at all we have our overall reaction from A to D, and we are going to call that one energy or delta H1. So delta H1 is the enthalpy change for the overall reaction. But when this reaction is taking place, we are seeing that there's a lot of enthalpy changes that are involved for that reaction to take place. And we are saying that by Hess's law, root 1 is going to be equal to root 3 or root 2. Root 2 is the one which involves all these reactions, or which involves all these enthalpy changes. And root 1 is the enthalpy change that combines the overall reaction. So according to Hess, we are going to be saying that enthalpy in root 1 is going to be equal to the enthalpies that are present in root 2. And therefore, delta H1 is going to be equal to all these energies, summation of all these energies. That's what Hess proposed. So delta H1 is equal to delta H2 plus delta H3 and then plus delta H4. Now here we are going to be saying that this implies that the overall enthalpy change for the process is going to be independent of the number of steps and path by which the reaction is carried out. And therefore, calculating the enthalpy change for any process can be done as long as a route for which the enthalpy change is known, as long as the route involved in each and every step of the enthalpies is going to be known in each and every step. So according to us, we are going to be looking at the examples and we are going to be doing our calculations specifically according to Hess's law. Now there is a second method that involves crossing out different reactants and products, but you're going to be handling our calculations specifically to Hess's law so that you can understand the core and the basis of such thermochemistry calculations. So example 1, we are going to be saying that calculate, and example 1 involving application of Hess's law. We are going to be saying that calculate the enthalpy of formation of methane, given that the enthalpy of combustion of carbon is going to be negative 393 kilojoules per mole, and that of hydrogen is negative 286 kilojoules per mole, and the enthalpy of combustion of methane is going to be negative 890 kilojoules per mole. So the solution for that is going to be, we are going to have our individual elements carbon reacting with the standard element hydrogen with methane. Now before handling such equations, you have to make sure that the equation is properly balanced for you to start drawing all these arrows. Make sure that the equation is properly balanced, the overall equation, you make sure that it's properly balanced and all the elements, all the compounds are in their standard state. Carbon must be in solid form, hydrogen must be in the gaseous form, and methane must be also in the gaseous form, since methane is a gaseous product. So the overall exchange is going to be called standard enthalpy formation of our methane, which we are forming. But in the question, they gave us standard enthalpies of combustion of all these individual elements. So what we do is that we write an arrow going downwards to show that we are going to be burning all these elements in excess oxygen. And burning each and every element in excess oxygen, we define that as standard enthalpy of combustion. So standard enthalpy of combustion of carbon in oxygen is going to be equal to negative 393. And also standard enthalpy of hydrogen in oxygen is going to be equal to negative 286. But notice that we pressed here 2 in front of this energy value. The reason for that is because we have 2 as a coefficient in terms of balancing our equation. So the enthalpy change, or the enthalpy of combustion for combustion of hydrogen was for 1 mole of water. But here we are having 2 moles of water. So that's why we multiply the energy value given in the question by 2, because we have this coefficient on water. And that's the science that we are going to be basing on. Now, standard enthalpy of combustion of methane, the arrow is going to be going this side. Because when you are combusting methane, what you get is that you get carbon dioxide and water. You looked at this in organic chemistry. If you burn any hydrocarbon, you're always getting carbon dioxide and water. And since you already formed them, that means that the arrow for methane is going to be going to the clockwise side. So according to Hess's law, Hess said that the overall enthalpy formation, which is present here, overall enthalpy formation, which is present above here, is going to be equal to the summation of all these energy changes that are involved in this downward step. So we're going to be saying that applying Hess's law, or from Hess's law, enthalpy formation of methane is going to be equal to standard enthalpy formation 1, which was the one for combustion of hydrogen, plus standard enthalpy of combustion 2, which was the standard enthalpy of combustion of carbon, and then plus standard enthalpy and then plus delta H3, which was the standard enthalpy of combustion of methane. Now we come and we substitute for each and everything. So H1, delta H1 is the same as negative 393. And H2 is the combustion of hydrogen, which gave us 2 moles of water. That's why I multiply the energy given by 2. Because we have 2 as a coefficient on water for us to balance up our equation. So it's going to be 2 times the given energy. Then here, we are going to be saying minus. Now the reason why we are saying minus, trying to rub off this. The reason why we are saying minus is because when you look at what you're given, when you look at this structure, everything here, you see that all these arrows are going to the anticlockwise side. And everything in thermochemistry that's going to the anticlockwise side is positive. And everything that is going to the clockwise side in this topic is going to be negative. So that's why this side we are adding, and when it comes to this arrow, which is going backwards, we subtract. So minus the energy for standard enthalpy of combustion of methane, simply because its arrow is going in a clockwise direction. So minus negative 890. Now you put everything in the calculator and you're going to end up with your final answer for standard enthalpy of formation of methane to be negative 75 kilojoules per mole. Now some of you have a tendency of forgetting the signs, especially if you get an answer which is positive on your calculator, you forget the signs. Now notice that you won't get any accuracy mark because we are dealing with thermochemistry and all values should carry an energy sign, which is either positive to indicate that the reaction was endothermic or negative to indicate that the reaction was exothermic. So proceeding, if at all we are to comment according to the answer that you have got, remember that we said that standard enthalpy of formation determines the stability of a given reaction, whether it's feasible or non-feasible. So here, according to the answer, the above reaction is going to be feasible simply because the standard enthalpy of formation that we calculated is negative, or it is exothermic. So once you get your final answer to be in terms of negatives, it means that such a reaction gave out energy or evolved energy. And any reaction that evolves energy, we call it, or we term it as an exothermic reaction. And such reactions are for formation of stable compounds. That means that such reactions are very feasible, or they are very spontaneous, and they can easily take place at room temperature. Now going to the example 2, we are going to be calculating for the enthalpy of reaction, of this equation. Now we are provided that if carbon reacts with hydrogen, we are going to be forming methane or ethene. And they're saying that the enthalpy for combustion of carbon is going to be negative 393, which is already standard, kilojoules per mole. And enthalpy of combustion of hydrogen is going to be negative 286 kilojoules per mole, which is also standard. And enthalpy of combustion of ethene is going to be negative 1393 kilojoules per mole. So looking at the solution, first of all, we first write our equation and we balance it properly. Likely enough, we are given the equation. So 2 moles of carbon in their standard state, which is the solid, reacts with 2 moles of hydrogen, still in its standard state, which is gas, to give us 1 mole of ethene. in its standard state, which is a gas. So you make sure that the equation is properly balanced and each and every element or compound that you have wrote is in terms of its standard state. So this is going to be either enthalpy of reaction or enthalpy of combustion, because both of them are the same for as long as you're having molar quantities of reactants reacting. So they gave us standard enthalpy of combustion of carbon. So that's why we are writing here oxygen. Now balancing up this equation, you get 2 carbon dioxide. And to get to carbon dioxide, that means that you're having 2 carbon atoms. That's why we play due to the 2 which was present here. And then to balance up oxygen, since you're having 4 atoms of oxygen, we place here 2 in front of this oxygen that we are burning carbon with onto its arrow. But you make sure that oxygen is also having a specified state, because when you're marking thermochemistry, we first look at the states of your reactants, because when you're starting this topic, we said what affects this. One of the factors affecting these reactions is going to be the amounts of the reactants or products involved, and also the physical states, or the normal states in which the elements exist in before reacting. So make sure that all your reactants are in terms of standard states. So we are putting here 2 in front of the negative 393, which is the enthalpy of combustion of carbon, because the enthalpy of combustion of carbon which was given was for 1 mole. But here we are having 2 moles. 2 moles of carbon dioxide being produced. So that means that you get this coefficient which is present here, and then you multiply it with the energy value which was given to get the total energy values. And similar applies to water. Combustion of hydrogen gives you water or liquid water. And since you're having a 2 here on 2 water, we place it here to qualify for the energy changes, or to give us the full energy change that was required, since negative 286 is only the enthalpy of combustion of 1 mole of hydrogen. Now since we're having 2 moles of hydrogen, we have to put here 2 in front of the energy value that was given, or simply pick the coefficient which is down here and multiply it by the energy value that was given. Now the standard enthalpy of combustion of ethene, the arrow has to reverse. So this arrow is always going anti-clockwise, because whenever we burn any hydrocarbon in chemistry, we form carbon dioxide and water, which we already have. So reverse the arrow and it goes clockwise direction. And enthalpy of combustion for that is not multiplied with anything, and so is as specified in the question. So in this case, it was negative 1,393 kilojoules per mole. So use Hess's law. So by Hess's law says that overall enthalpy change for this reaction is equal for all these energy changes that are involved in this reaction. So trying to clear up our charts. We are going to remain with, so according to us, we are going to say that enthalpy of reaction. So from Hess's law, or applying Hess's law, this enthalpy of reaction, which is denoted by delta H alpha R, is going to be equal to these energy changes that are involved. Enthalpies of combustion for carbon, enthalpies of combustion for hydrogen, and enthalpies of combustion for ethene. Since Hess's law says that overall enthalpy of a reaction is equal to the summation of all these individual steps that are being involved in such a chemical reaction. So standard enthalpy of reaction is equal to enthalpy of combustion of hydrogen plus enthalpy of combustion of carbon plus minus. We are saying that minus because if you look at this arrow is going clockwise, and we say that anything going clockwise in a clockwise direction is subtracted from those ones that are going in anti-clockwise. So those ones that are going anti-clockwise are added, and anything that is going clockwise are subtracted. So that's why you are seeing a negative here. So you have to pay attention to that. So standard enthalpy of formation is equal to summation of those ones that are going anti-clockwise minus summation of those ones that are going clockwise. So that's why you're having such an expression. Then substituting, you make sure that you retain the energy values on the values that you're using, because that's when we shall determine, or we shall know that you are still dealing with energy. The moment you eliminate these values and you don't use them, we shall take an assumption that you are not dealing with energy values, and you get everything wrong. So putting everything in the calculator, you're going to end up with your enthalpy of reaction to be equal to positive 35 kilojoules per mole, which is the required answer when you apply Hess's law. Now, making a general comment about the above calculated answer, since we have got our standard enthalpy formation in terms of a positive value, that means that such a reaction is endothermic, or energy is required for such a reaction to take place. And now, once energy is required for such a reaction to take place, we say that the above reaction is not feasible, simply because the standard enthalpy of formation or the standard enthalpy of reaction is going to be, or we have obtained it as a positive value. It means that such reactions require energy to take place. So that means that without energy, they cannot proceed. So that's why whenever you get your standard enthalpy of formation of any compound in terms of positive, they are going to ask you to comment about your answer. And your comment is going to be simply that such a reaction is non-feasible, or is not spontaneous, or it cannot proceed, because the standard enthalpy of formation you have calculated is simply endothermic, or you can just say is simply positive. So looking at example 3, we are going to be saying that the thermochemical data for some reactions at 298 Kelvin are given below. Now, Roman number 1, combustion of carbon monoxide in oxygen gives you carbon dioxide, and the energy change for that is negative 283 kilojoules per mole. And then combustion of hydrogen in oxygen gives you liquid water, and the enthalpy change for that is negative 286 kilojoules per mole. And combustion of methanol in oxygen or in excess oxygen is going to give us carbon dioxide and water, and the enthalpy change for that is negative 715 kilojoules per mole. Now we are required or prompted to calculate for the enthalpy change for the following reaction when you react carbon monoxide with hydrogen to form methanol. So let's look at the solution under that according to Hess's law. So looking at the solution, we are going to say that first of all, write our equation balanced. That's the first thing. So write carbon monoxide gas in all elements, all compounds must be in their standard states. So carbon monoxide or gaseous carbon monoxide reacts with 2 moles of gaseous hydrogen to form liquid methanol. And the overall reaction is called standard enthalpy of formation of methanol, or you can simply call it standard enthalpy of reaction. They're the same. So burning carbon monoxide in oxygen is what we call as standard enthalpy of combustion. And the reaction of this the oxygen must be in its standard state, and the oxygen must be balanced. So when you burn carbon monoxide in oxygen, we get carbon dioxide gas. So we get gaseous carbon dioxide. I say that when you're marking these things, all this diagram is going to carry 3.5 marks. But those 3.5 marks, to obtain them, you must have standard physical states. And after that, your equation must be well balanced. And after that, all the oxygen atoms that you're including on your arrows must carry oxygen states. And after that, the energy values must be multiplied with the specific coefficients that are present in your products. So you're saying that here, when we burnt hydrogen in oxygen, we formed 2 molecules of water. That's why we got its energy value and we multiplied it by 2, simply because you're having a 2 as a coefficient on water. And for that of carbon monoxide, we burn carbon monoxide in oxygen to form carbon dioxide gas or gaseous carbon dioxide. And methanol, we burn it in oxygen to give whenever we burn hydrocarbons in oxygen, we always get carbon dioxide and water, and its arrow, or the arrow on combustion of the product, is always going in a clockwise direction. And the enthalpy of combustion is not touched or is not multiplied by anything. So it remains the way it is, or it was dictated in the question, which was negative 715. So applying Hess's law says that this overall reaction, the enthalpy for this overall reaction is equal to all these energy changes that are involved in this way. The energy changes that are going anti-clockwise, we add them, and the energy changes that are going clockwise, we subtract them. So that's why standard enthalpy of reaction or formation of methanol is equal to the standard enthalpy of combustion of hydrogen plus standard enthalpy of combustion of carbon monoxide, and then less standard enthalpy of combustion of methanol, simply because we are saying that minus because the arrow for standard enthalpy of formation of methanol is going in a clockwise direction. So we sum up those ones that are going in in an anti-clockwise direction, and we list those ones that are going in a clockwise direction. After that, we make the appropriate substitutions according to the energy values that are present on our arrows. So I'm going to have 2 multiplied by negative 286. I say that including the signs is very crucial because it indicates to the examiner that you are dealing with energy changes. Then plus negative 283, and then minus or less negative 715. And putting everything in the calculator, you're going to end up with your standard enthalpy of reaction or formation of methanol to be negative 140 kilojoules per mole. Now, if you're required to comment about such an answer, since you have got your standard enthalpy of formation or reaction to be negative, that means that such a reaction is very feasible, or is feasible, or it's spontaneous. Simply because your standard enthalpy of reaction or standard enthalpy of formation is negative, or someone can say it is exothermic. So that means that such a reaction is very feasible. Now you're going to pause the video, you pause the video and you take down these questions. Now you make sure that you discuss them with your friends and try out each of the numbers individually. You must end up with the final answers that are specified in these brackets here. So you pause the video and you try to take the numbers, you try to assess your understanding according to the given examples. So pause the video, and by the way, share the video to your friends so that you can all benefit as a group. It's better when you all succeed together. So pause the video and take the questions. So now we are going to be looking at the other energy changes that are going to be helping us in proceeding with other types of calculations or handling several calculations that are involved in thermochemistry. And we are going to be looking at the standard enthalpy of atomization. Now these energy changes, they are going to be very crucial when we come to energy level diagrams together with Born-Haber cycles. And looking at standard enthalpy of atomization, we are going to be looking at it as the required heat or energy required. You either say heat required or energy required. So always remember that for us to atomize anything, we need energy. So you should be very conscious about that. It's not an enthalpy change. It's always the energy required or heat required. So it requires to convert any substance or any element that is present in its normal state or in its normal physical state under standard conditions of temperature and pressure into 1 mole of gaseous atoms in gaseous state, or into 1 mole of atoms in the gaseous state, or someone can say into 1 mole of gaseous atoms. So energy required to convert any substance or any standard element that is present in its normal state into its constituent gaseous atom or gaseous atoms is called enthalpy of atomization and is denoted by delta H with a subscript of atomization of a specific element that you are dealing with. So if you want to atomize hydrogen, you must form 1 mole of a product. So for us to form 1 mole, that's why you are seeing that you are balancing these equations with a half. So any heat required to convert 1 mole of a substance in its normal state into its constituent gaseous atoms under standard conditions is going to be named as enthalpy of atomization of any given element. Now from there we are going to be looking at bond dissociation energy. Now bond dissociation energy can also be the same as bond energy. But for bond energy entangles both dissociation and it also entangles both formation. So bond energy can be defined in terms of formation or it can be defined in terms of dissociation. But if at all it is specified like bond dissociation energy, now this one is in terms of dissociation completely. And we are going to be saying that for a diatomic molecule, this is going to be the heat required to break 1 mole of a covalent bond into its constituent gaseous atoms. So you have to add that extension. Heat required to break 1 mole of a covalent bond of a diatomic molecule into its constituent gaseous atoms. For example, if you're having hydrogen gas, the heat required to break the bond holding these two molecules or these two atoms in this molecule to form the two atoms separately is going to be called bond dissociation energy, which is denoted by BDE of hydrogen, and the same applies to chlorine. So the heat required to break 1 mole of a covalent bond of a diatomic molecule into its constituent gaseous atoms is going to be called bond dissociation energy. So also note that just as the same as atomization energy, it's also going to be heat required or energy required. So bond dissociation energy is going to be the energy required to break 1 mole of a covalent bond of a diatomic molecule into its constituents or into its constituent gaseous atoms, and it's going to be denoted by BDE. Like I said, all these energy changes are going to be very important when you come to Born-Haber cycles and energy level diagrams. You need to understand them properly. So you're saying that from two energy changes above, for a diatomic molecule, it can be seen that enthalpy over time atomization is always going to be half of the bond dissociation energy. So remember that for bond dissociation energy, it gives us two atoms. So that means that if you want energy for one atom, which is called enthalpy of atomization, we are going to get it by halving the bond dissociation energy. So note this expression is very important when it comes to energy level diagrams, which are very common. You are either given bond dissociation energy and you are required to find atomization energy, or you will be given atomization energy when you are required to find bond dissociation energy. So always know this: for you to get atomization energy for one atom, you get bond dissociation energy, you divide it by 2. And the reason for that is because bond dissociation energy involves energy of 2 atoms, and atomization energy involves energy of only 1 atom. So for us to get atomization energy, we have bond dissociation energy, so that you can get the energy that is contained by 1 atom. So that's why we give this expression by saying that atomization energy is equal to half the bond dissociation energy. So proceeding, we are going to be saying that bond energy, therefore, is going to be the average amount of energy required to break a bond of 1 mole of a substance into its constituent gaseous atoms. Now we are saying that here, bond energy required to break a bond to form the same bond is going to always be the same. Bond breaking is going to be requiring energy, and therefore it's going to be an endothermic process or an endothermic reaction. When you're breaking any bond, energy is required, but when you're forming a bond, energy is given out. So that's why we are saying bond breaking is an endothermic process, whereas bond forming is an exothermic process. Now looking at the factors affecting average bond energies, they're going to be including the following. And the first one is going to be the bond energies are going to depend on the following. We gave a variety of factors, however, we gave out 2. So the first one, we are going to be looking at bond length. And by talking about bond length, we are talking about atomic radius of the individual atoms that are involved in a given molecule. So if it's fluorine, we shall look at the atomic radius of the 2 atoms that give us the fluorine molecule. So I look at the atomic radius of the fluorine atom, the 2 fluorine atoms separately, to determine the strength of the bond. So that's why we are saying that bond length here is going to be determined by atomic radius of the bonding atoms that are present in a diatomic molecule. So the larger the atomic radius, the larger the atomic radii of the bonding atoms, the longer the bond becomes. And in inorganic chemistry, we say that the longer the bonds, the weaker they become. And therefore, the larger the atomic radii of the bonding atoms, the longer the bonds become. And the longer the bonds, the weaker they become. And therefore, bond dissociation energy for such a diatomic molecule is going to be very low or very low. So part B, we can also look at number of bonding electrons. Now we looked at these ones under metals when you're explaining group 2 elements. And we say that The more the number of electrons that participate in formation of a particular bond, the greater the strength of that bond, and therefore the bigger the value of the bond dissociation energy. For example, if you're having a triple bond and a double bond, we expect a triple bond to be stronger than a double bond, because in a triple bond there is more bonding electrons that are involved to form the triple bonds, but in a double bond there are fewer bonding electrons that are involved to form it. So we expect triple bonds to be stronger, or triple bonds are more likely to be stronger than the double bonds, which in turn is stronger. Also, the double bond is going to be stronger than the single bond, because the lower the number of bonds, the lower the bonding electrons that are being involved. So the greater the bonding electrons involved, the stronger the bond gets, and the lower or the lesser the bonding electrons involved, the weaker the bond length or the bond strength of such a diatomic molecule becomes. So looking at another energy change, you're going to be looking at the standard enthalpy of sublimation. And for standard enthalpy of sublimation, is quite the same as standard enthalpy of atomization, but in this case we are going to be dealing with solids. So sublimation only deals with solids being converted to gases. So you're saying that standard enthalpy of sublimation is going to be the energy required. So also this process requires energy. It's not enthalpy change. Most of you lose marks because of the word enthalpy change. These reactions are specific in nature. There are those ones that require energy, and there are those ones that give out energy. And there are those ones that do both, like standard enthalpy of formation or standard enthalpy of reaction. But you need to be very specific when you're defining others. So energy required to vaporize 1 mole of a solid element which is present in its normal state or in its normal physical state under standard conditions into gaseous atoms is going to be called standard enthalpy of sublimation. So energy required to vaporize 1 mole of a solid element which is present in its normal physical state into its constituent gaseous atoms at standard conditions. And it says that standard conditions are going to be 1 atmospheres and 298 Kelvin. So you can either define them or you can simply say under standard conditions. So whenever you're having a solid getting converted into a gas, we call that one standard enthalpy of sublimation. Solid into a gas, we call that one standard enthalpy of sublimation. Carbon solid into carbon gas, we call that one standard enthalpy of sublimation. And we are taking note that for solid elements, enthalpy of sublimation is going to be equal to enthalpy of atomization. Like I said, enthalpy of sublimation can be the same as enthalpy of atomization for solid elements, but enthalpy of sublimation can only be used where atomization is from a solid to gas, as you are going to be using them in your lattice energy level diagrams or energy level diagrams, as we are going to be looking at Born-Haber cycles. So we are saying that enthalpy of formation together with atomization and enthalpy of sublimation can be determined or can be used to determine the mean or average bond length or bond energies of the bonds that are involved in unlike atoms. For example, if you look at this question here, we are going to be saying that, or is prompting us to determine the average energy of silicon chloride. But the question goes that standard enthalpy change for the formation of silicon chloride is negative 610 kilojoules per mole, and the standard enthalpy changes of atomization of both silicon and chlorine is going to be positive 338 and positive 122 kilojoules per mole. Both of them are positive because we said that for us to atomize anything, we require energy. So that's why you're seeing a positive here. And some questions are very funny, whereby they want to give you this positive to be there, where they want you, or the examiner wants you to know that atomization requires energy. So we are supposed to use these values to construct a Born-Haber cycle for the formation of silicon chloride from its elements, and we indicate the energy changes that are getting involved. So let's look at the solution under that. So for such reactions, first of all, we first write a balanced equation for the formation of silicon chloride, and that means that we are going to react solid silicon together with gaseous chlorine to form silicon tetrachloride, which must be liquid. We say that all group 4 tetrachlorides are liquid in nature because they are covalent in nature and they have simple molecular structures. So the enthalpy of formation of silicon tetrachloride was given as negative 610. So here, before these elements react, both of them must be in terms of gaseous state, or they must be in terms of atoms. So what we do is that we atomize silicon to get silicon in its gaseous state. So from solid to gas, positive 338 is the standard enthalpy of sublimation of silicon as an element to gaseous silicon. So standard enthalpy of chlorine as an element to gaseous atom. So this one, chlorine here, is in terms of a molecule, but for it to undergo reaction, it must be in terms of atoms. So that's why you're having here 4 chlorine atoms. According to the balanced equation, we have here 4 chlorine atoms up here. That means that they also have to be 4 down here. That's why you're having a coefficient of 4 on chlorine atom. Now we multiply the energy, or we multiply the energy for atomization of chlorine by 4 because the one that was given was for an atom. So I pick the coefficient which is present here and multiply it by the given value that was present in the question so that we can get the overall enthalpy of atomization of all these 4 chlorine atoms that we're having here. Now combining these 2 atoms gives us what we call silicon to chlorine bond energy, and those bond energies are going to be 4. They're going to be 4 because we're having 4 chlorine atoms here and 1 silicon atom. So 1 silicon atom is going to be covalently bonded to 4 chlorine atoms. So that's why we are putting here 4 bond energies of silicon chloride to give us this. So if you look at this, this diagram, all our arrows are going anti-clockwise. And if all our arrows are going anti-clockwise, we are going to be applying S0, and you're going to be saying that this energy is going to be equal to the summation of all these values. Now in the enthalpy of combustion, we were always lessing the value which was going on this arrow, simply because the arrow in enthalpy of combustion is always clockwise. But here, in bond energies, the arrow is going anti-clockwise. So that means that enthalpy of reaction, overall enthalpy of reaction is going to be equal to the summation of all these bond energies without subtracting any, just like it was in enthalpies of combustion. So that means that negative 610 is equal to the summation of positive 338 plus 4 into positive 102 plus 4. We are saying that plus because the arrow is also anti-clockwise, plus 4 of the bond energies of silicon to chlorine. So summing up that and making 4 bond energy of silicon chloride the subject, we are going to end up with, on the calculator, negative 1436. So we divide through by 4 to remain with the bond energy of silicon to chlorine, or which is called the average bond energy of silicon to chlorine. You get it by dividing the number of bonds that you are having by the energy value that you have got. So total energy value divided by the number of bonds contained give us the average bond energy. And if you get negative 1436 divided by 4, you're going to end up with your bond energy to be equal to negative 359 kilojoules per mole as your average bond energy of silicon to chloride bond. So having the same question, we are going to be looking at some of the enthalpies that are being given here. And some of the enthalpies of certain reactions are given below. So sublimation of carbon to gaseous carbon is going to be positive. Energy required is going to be positive 713 kilojoules per mole. And atomization of hydrogen molecule to its gaseous atom, the energy required is going to be positive 436 kilojoules per mole. And atomization of carbon, or reaction between the carbon as in its standard or in its normal state with hydrogen, we are going to be forming methane. So this is our general reaction, and these are going to be the atomization reactions. So make sure that you place them in terms of Hess's formula so that we can determine the average bond energy. Average can also mean mean. So that's why here we are prompted to calculate for the mean bond energy that is formed with methane. And let's look at the solution for that. So you're going to start by writing a well-balanced equation for the formation of methane gas. So solid carbon dioxide reacts with gaseous hydrogen to form methane. So the first thing, we first write a balanced equation and write the overall enthalpy of formation of methane, which was given as -63 kJ per mole. But before these elements reacting, since we are given enthalpies of atomization, we have to convert them into their respective atoms. So enthalpy of sublimation of carbon is going to be equal to, it was given as positive 713. And then for enthalpy of atomization of hydrogen, enthalpy of atomization of hydrogen, we are given bond dissociation energy. And bond dissociation energy, remember, is the same as a half the atomization energy. So we are putting here 2, putting here 2, it would have been 4, multiplying this bracket. But since we are given, for us to get bond dissociation energy, or for us to get atomization energy, we get the bond dissociation energy divided by 2. But remember that this 4 here, we have to multiply it with the energy that was given. So there was a 4 here initially. So what we did is that we crossed these 2, and we got 1, and we got here 2. So we converted bond dissociation energy into atomization energy, which is going by halving bond dissociation energy and getting the coefficient T on the hydrogen gas atom, and multiply it there so that we remain with 2 into positive 436. So this step is very important to understand, because you are given bond dissociation energy and you have to convert it to atomization energy. And we say that atomization energy is half the bond dissociation energy. Now after getting the atomization energy, you have to multiply it by this 4. So they have crosses, or the 2 crosses with this 4, to remain with 2 into positive 436. So that is the bond energy, or the atomization energy for all these 4 hydrogen atoms. Now the energy that is evolved when we form a bond between these gaseous atoms is going to be called the bond energy for carbon and hydrogen. So write it in this form. And I say that there are going to be 4 bond energies, or the 4 bonds for carbon and hydrogen formed, simply because we're having 4 atoms of hydrogen here. So since we're having 4 atoms of hydrogen here, we expect that carbon is going to form in methane. Carbon forms 4 bonds of carbon to hydrogen. If you sketch that out, or if you draw its structure of methane, you are going to find that the carbon to hydrogen bonds are 1, 2, 3, and 4. So that's why we are writing 4 carbon to hydrogen bond energy to give us methane gas. Now, since all arrows are going anti-clockwise direction, so we're going to say that according to Hess's law, this overall enthalpy of formation is going to be equal to the summation of all these enthalpies of formation in this reaction. So we're going to be saying that applying Hess's law, enthalpy of formation is going to be equal to enthalpy of sublimation of our carbon plus twice the bond dissociation energy, which we already got here, according to the way I explained to you, then plus the bond energy of carbon to hydrogen. So substituting for the values and putting everything in the calculator, taking this one this side, you're going to end up with negative 1648 to be equal to the bond energy of carbon to hydrogen. So for us to get mean or average bond energy, we divide through by these 4 across all sides, so that we can get the average bond energy for a single carbon to hydrogen bond, which is going to be negative 1648 divided by 4 to give us negative 412 kilojoules per mole as the average bond energy for the carbon to hydrogen bond. So we're going to make a conclusion that the average or mean carbon to hydrogen bond energy is going to be negative 412 kilojoules per mole. So let's go through example 3 real quick, as we already have the knowledge about what is being required. So this is the general reaction. This is enthalpy of atomization of hydrogen. This is enthalpy of sublimation of our carbon. I say that enthalpy of sublimation only works for solid compounds, and others are going to be applied to enthalpy of atomization. So writing the general equation, which is well balanced, is going to be this one. And you're also given bond dissociation energy. So you try to convert bond dissociation energy into atomization energy. So all these ones are bond dissociation energies that you are given. So since we are given bond dissociation energy, you have to convert it into atomization energy, just like we explained before. But here, these ones are atomization energies. There's nothing like bond dissociation energy here. So you try to remove this element that is trying to confuse. However, for hydrogen, it was bond dissociation energy. Because if you look in this equation here, if you look in this equation, they have told you that this energy, or the positive 436 kilojoules per mole, was formed for 2 moles of gaseous atoms of hydrogen. So if at all 2 moles of gaseous atoms of hydrogen contain this energy, then what about 6? So you'll find that if 2 moles contain 436, for you to get energy contained by 6 atoms of hydrogen, you get the energy that is being given multiplied by 3. So you do the math. If 2 moles contain positive 436, then what about 6 moles? So you end up with your value to be 3 into positive 436. So here, enthalpy of sublimation of carbon is going to remain the same. We get the 2 which is here. We multiply it with the enthalpy of sublimation that was given. And then here, now here we are forming 2 types of bonds. If you sketch this structure, you are going to end up with carbon-to-carbon bond being attached to different carbon to hydrogen bonds. So you find that we are having 1 carbon-to-carbon bond, and we are going to be having 6 carbon to hydrogen bonds, which is going to be our average bond energies. So we are going to apply a system, and you are going to say that overall enthalpy of formation is going to be equal to the summation of the enthalpies that are involved in the different states that are involved when this reaction is taking place. So we substitute for everything, and you're going to end up with negative 84 being equal to twice into positive 713, then plus thrice into positive 436, plus the bond energies of carbon and hydrogen together with carbon and carbon. So if you make the bond energies the subject, you're going to remain with negative 2818. You're going to remain with negative 2818. So try to make one the subject. So, but remember, from example 2, we had already got the average bond energy for carbon to hydrogen. So we are going to make one of them the subject. So since the average bond energy for carbon to hydrogen is known as negative 412 kilojoules per mole, we substitute for it. And we are going to end up with 6 times negative 412, and then we remain with carbon to carbon bond, which we make the subject by taking this one this side after multiplying. And we are going to end up with, if this one goes this side, it's going to become a positive. So we are going to end up with the average bond energy of carbon to carbon bond to be negative 346 kilojoules per mole. Now notice that most of the energies, or most of the bond energies involved in formation, from atoms to formation of bonds, energy is going to be evolved. So that's why you are seeing that most of the answers that we are having were in terms of negative. Reason being, bond formation involves release of energy, and bond breaking involves requirement or absorption of energy. So you're going to pause the video and you take down these notes or these questions to ascertain your understanding, and make sure that you try to discuss them with your friends and take them to the teacher for analysis to ensure that you have properly understood the skill of solving such numbers. So pause the video and try to take these numbers. Now another simple task that we are going to be dealing with enthalpies of formation, which is finalizing this video, is calculation using formulas provided when you are given enthalpies of formation. So we are going to be calling these ones predictions of enthalpies of a reaction from enthalpies of formation. Now you are saying that here, the knowledge of standard enthalpy of formation of various substances can be used to calculate the enthalpy of reactions under specific conditions, which must be standard. So provided you have this reaction or reaction equation, we are saying that you can get enthalpy of any reaction by simply getting summation of all the enthalpies of formation of your products and you less summation of all the enthalpies of formation of your reactants. Now this formula is very common, and all these questions that carry this formula are set in paper 1, and they are mixed together with chemical equilibria. So for you to be good at chemical equilibria, you must even be very good at understanding this formula, because they are going to be brought together in conjunction in each and every paper 1 chemistry paper that you'll be holding. So enthalpy of reaction for this equation, if you look at overall summation of enthalpy of formation of our products, is going to be equal to summation of enthalpy of formation of SC, which is our product 1, plus enthalpy of formation of BD, which is our product 2, then minus overall enthalpies of formation of our reactants. And our reactants were enthalpy of formation of AB plus enthalpy of formation of CD. So you are going to note that standard enthalpy of formations of elements is going to be equal to 0, like magnesium. Magnesium is a solid, it cannot be formed. So always such, even the question, they are not going to prescribe them. They are going to leave them undefined. So don't say that they have not given you such values, but you need to understand that all elements that exist in nature, their standard enthalpy of formation is 0, because there's no way you can form them when they exist. So standard enthalpies of formation of all gaseous compounds, of most of the gaseous compounds, like oxygen, like any element, like magnesium, which is a solid, for as long as it does not involve combining two elements, standard enthalpy of formation is always going to be equal to 0. So example under that, a given example, you are given that standard enthalpy of formation of methane is going to be negative 63 kilojoules per mole, and that of ethane is going to be negative 84 kilojoules per mole. Now you are being prompted to calculate for the standard enthalpy of change for the reaction below when you hydrogenate ethane to form propane or to form methane. So we are going to write our formula, since we are given values, that for us to get enthalpy of any reaction, we get summation of standard enthalpies of formation of our products, and you less standard enthalpies of formation of your reactants. And we substitute for that by saying that it's going to be 2. Now, according to the equation, we are saying that 2 times 63, because there is a 2 here on the coefficient of methane. So 2 times negative 63, which is the standard enthalpy of combustion of our product, and then plus minus standard summation of all standard enthalpies of formation of your products or your reactants. So for that one of ethane was negative 84. Now we are saying that plus 0 is for hydrogen, because hydrogen exists in nature, there is no way it can be formed. So therefore, hydrogen does not have standard enthalpy of formation. We shall just put there 0 as its standard enthalpy of formation as a reactant. So putting everything in the calculator and simplifying, you're going to end up with your standard enthalpy of reaction to be negative 42 kilojoules per mole. Now you're advised to pause the video and you take down all these questions. Try them, discuss them with your friends to make sure that the concepts that you have learned in this video sink. Now you're going to be proceeding with the next videos, and we are going to be proceeding from bond energy, and we deal with the calculations that involve bond energies. For now, this video is enough for you to ascertain what you have got under thermochemistry, discuss with your friend, and try out these numbers. The answers are provided, and if you feel that you have any urgent issue, simply reach out to your teacher, or try to reach out someone who is at your school and is above you, or try to reach out me in case you're having any challenge in accessing these videos or the content that is present on this video. So pause the video and write down all these questions. Now this brings us to the end of this video. You're advised to share the video to your friends, subscribe to the channel, and share the video to your colleagues so that you can all benefit as a family. Those of you having paper success in your examinations. See you in the next video.